Welcome back to Dave Does Math from Home. This is part 3 of our video series on path independence, section 17.3. Videos 1 and 2 were chunky videos. They were sizable slabs of content, and in them we talked about what path independence means, and we talked about a quick test to determine whether or not something was path independent, and then we talked about if it is path independent, how you can find the potential function whose gradient is that vector field. So the last thing that we still need to talk about is what are we actually doing with those potential functions? There has to be some benefit to this. Like, we can't just find the potential function and be like, there it is. Cool. It's that one. We're going to be doing something with those potential functions that's going to be much, much easier than your typical line integral. So I wanna retreat to some of the other things we did. Let's just start with the one that we just did in section 2. We had the vector field was 8x y cubed. I probably just shouldn't have erased it at all. 12x squared y squared. Okay. In the last video, we looked at this vector field. We determined that it was path independent, and then we further determined that the potential function for it was 4x squared y cubed, possibly plus c. So here's the huge benefit of path independence, and here's why we've been doing this and why it's important. If I had asked you to do a line integral, let's say find line integral over c f dot dr between, say, c is the zigzag from 1, 1 to 3, 2. So we have this vector field doing its vector field stuff. We have a point here at 1, 1 and a point here at 3, 2, and we want the zigzag, so something's going to zigzag like this. And some of you might be looking at the zigzag and saying, how am I supposed to parameterize that? That's nonsense. And I say, yeah, it is nonsense, but the parameterization doesn't matter. This thing is path independent. So here's the big payoff. If you know that this vector field is path independent, and then you can find the potential function, the only thing you need in the potential function is the start and the end point. In many ways, this potential function is like the integral of this vector field. So if someone asks you to take the integral of the vector field, we can say, instead of doing the line integral, f dot dr, I can just do like the normal integral evaluated at the end point and evaluated at the starting point, and it's the difference. Hopefully this reminds you a lot of the fundamental theorem of calculus that when we first learned it in Calc 1, we said instead of trying very hard to like calculate the area under curves, you can take an antiderivative and evaluate it at the end and the start and subtract them, and that's how you get your area. This is sort of the same thing. Instead of doing the line integral across this path to see what's happening, we have what is essentially the antiderivative here. Phi is the antiderivative, and you evaluate that at b, you evaluate that at a, and that's it, you're done. So the potential function evaluated at b is, what is this, 4 times 9 times 8. That's actually kind of a big number. That's fine. And the potential function evaluated at 1, 1 is 4 times 1 times 1. That's also kind of why C doesn't matter, because just like in Calc 1, when we first started doing antiderivatives, we would say you have to include the C, there's an arbitrary constant. And then when we started to do areas, like actual integrals, areas under curves, we said the C doesn't matter. When you evaluate this integral at the start point and the end point and subtract them, that C is going to cancel itself out. So you can sort of not worry about it. The same thing is happening here. If we evaluate this at B, and there's a plus C here, and then we evaluate it at A, and there's a plus C here, and those things cancel out, you can effectively just ignore the C's the whole time. That's the arbitrary constant C, not the path C. This C is for curve, that C is for constant. So whatever this is, 36 times 8 is probably going to be 240 plus 48, so 288, I guess. 288 minus 4 is 284. Bam. Line integral finished. So hopefully that's a shortcut over trying to figure out what this zigzag thing is doing. Let's do one more of these, and then I will call it good. And again, I want to use one that we've sort of already done. So let's look at vector field equals 3y plus sine of x, 3x plus 16y. And this was the first one we did, and we determined that it is path independent and that the potential function is 3xy minus cosine x plus 8y squared. So if someone was to ask you to find the line integral, or the path integral, f dot dr, where c is, what do we want c to be? Let's just have c be a straight line. For c, I won't even explain the path, because it's path independent. Path doesn't matter. C goes from let's start at 0, 1, and let's end at pi, 4. So instead of doing the line integral, I'm just going to evaluate what is effectively, let's see, sure. I'm going to evaluate what is effectively the antiderivative at the start and the end point. And subtract them. So evaluating this at pi is going to give me 3 times pi times 4, so that probably is going to be 12 pi, minus the cosine of pi plus 8 times 16. This is me evaluating at pi comma 4. So this is phi of b. And from this I need to subtract what happens when I evaluate this at 0, 1. This is going to be 3 times 0 times 1, it's probably 0, minus the cosine of 0 plus 8 times 1. So I have 12 pi minus cosine of pi means plus 1. 16 times 8 should be 2 to the 7th, so 128. Minus 0 minus 1 plus 8. So I'm subtracting 7. So this is 129 minus 7 to 12 pi plus 122 is the antiderivative, or is the line integral. So this lets us do line integrals without ever actually doing line integrals. I know that line integrals are super easy because we can do them in 5 easy steps or your money back guaranteed, but this I think is even easier. Perhaps you were not expecting the final sections of Calc 3 to be easier than the other stuff we've done. But I think this is great. I think this is a really powerful tool. So when you do the homework for section 17.3, it's going to sort of go through the process that we just did very slowly. There's going to be a lot of questions like, is this path independent? And it just wants you to do that derivative test to see about the mixed partials matching. And then there's going to be questions like, if it is this path independent? And if so, what's the potential function? And that's what you'll be doing. That's when you'll be doing the stuff we did in the second video where we determine if it's path independent, and then if so, we find the potential function by doing the integrals with the unknown f of x pieces and the unknown g of y pieces and trying to make those match. And then at the end, there's going to be a couple questions where it asks you to do these line integrals using this shortcut, which is very nice. So homework, very straightforward, very clear. Here's sort of the bad news. When I write tests and quizzes, I'm going to be a lot less forthcoming with information. So on the quiz for this section and on the test that we take in a couple weeks for our final exam, I want you to expect to see some line integrals. And some of those line integrals will be things where I want you to do the full line integral, 5 easy steps. Just do the line integral. It's taken care of. Some of those line integrals are going to be line integrals over vector fields that are path independent, where if you just do the line integral, if you just sort of like brute force it, you'll get through. It'll be hard, but it'll be doable. It'll just kind of be a waste of time on your final. If you check for path independence and you find that it is path independent and you use this shortcut, it's going to be much faster and much easier, and it's going to leave you a lot more time for the rest of the exam. And I'm not going to tell you which one to use. This is me expecting you to know the shortcuts or know when to apply the shortcuts, because we have a test for that. There's a test for whether or not you can do the shortcuts, and the test is very easy. So I'm going to expect you to know this test and like be able to apply this test to problems, and then I'm going to expect you to be able to remember the shortcut and do the shortcut to make the problem really easy. It's up to you. I believe in you. That's the end of this video. We'll see you in class.